Yeah, thanks for the invitation. Thanks for the introduction. I'm Yijie Shen from NTU Singapore, and I'm very happy to be here to share our recent work on topological photonic quasiparticles. Let me start with some basic concept about topology. What is topology? I think topology is a fantastic mathematical branch studying the preserved property of an object through continuous deformation. What is continuous deformation? For instance, look at the cup can be continually deformed into a ring or donuts. However, no matter how we can shape the geometry, there are some preserved property. For instance, how many holes? There are always hole inside, right? It's always a hole inside, and this is similar to a swimming ring. But these objects are fundamentally different with, for instance, a sphere, a ball without hole, and also distinguish with glasses with two holes. So how many holes? The number of holes acts as a topological invariance to distinguish the object with dramatically different properties. So this is very useful ideas and very useful methodology to distinguish, to classify the different object with fundamental different properties. This is very important for fundamental physics. I think we are very familiar with the Nobel Prize in 2016 for the topological phase in materials, topological insulator. But here I will share the story of topological physics in particle physics, and it's also very famous with the stories from the UK scientist, particle physicist Tony Skyrmion. In 1960s, this Skyrmion proposed very beautiful mathematical model to unify a large class of large family of fundamental particles using topological idea. This is his idea. Idea is using a stereographic mapping from a spinning sphere. Since that's like you unwrap a spinning sphere onto a localized 2D plane, you can have a spin texture. Okay, just like you can arrange your hair, the hair is your hairy head, the hairstyle into different style, you can arrange diversified spin textures. You comb your hair around, you get a vortex, so we call it block type spin texture. You can also arrange some bundles, similarity on the spinning sphere, get some other kind of spin texture. And the diversified spin texture can be characterized by the topological invariance. It's called Skyrmion number. For instance, the hedgehog-like texture directly unwrapped from a sphere, you get Skyrmion number of 1, so it's a neotype. And this same topological number as the block type vortex. That means these two kind of particles are similar. They can transform to each other. Just so you can comb your hair around, you can transform the texture. But however, it's very difficult to transform to anti-Skyrmion. That's with sidle-like texture, right? And with the very different Skyrmion number. So this is a very important, extremely important concept for our information society, because now we can have a diversified topological numbers in the very localized and small particle region. And if that can be realized in the magnetic materials, this will promise the high density data storage with the topological number as the information carrier. And indeed, it's really a hot topic, and people are more producing diversified Skyrmion particles topologies in the diversified condensate in magnetic material density, the condensate and the liquid crystals, and also with the more complicated controllable topology from Skyrmion lattices. You can have an array of topological number, the Skyrmion bag with large topological number, Skyrmion bundle, Skyrmion breed with the 3D topology. Anyway, all of these are in solid state physics, right? But today I will focus on even novel concept of optical skyrmions. That means constructing skyrmion texture in using optical vector field. It's very different from the solid state physics skyrmions. The initial works on this field from plasmonic surface. How to shape skyrmion texture in light? The initial idea is to produce the evanescence field on the structured surface plasma, and on the surface plasma polarity field can support the evanescence field on the surface with not only in-plane electric field component out of plane component. This will possible to shape the electric field as a skyrmion-like texture. Soon after, other kind of optical field, for instance, spin angular momentum vector, that's also can be shaped onto a surface, metal surface, to shape an isolated skyrmion texture. And soon after, the many other kind of diversified topology fractional maroon texture was shaped. However, these are all limited in 2D surfaces, right? No matter how you shape your light, they are all limited in a surface on 2D plasmonic surface. So my idea is to break this limit, to apply a higher dimensional structural light to shape skyrmion texture in free space, and then I will deliver 3 kind of free space skyrmion in our recent works, and I will introduce them one by one. And the first one I call it Stokes skyrmion. What is Stokes skyrmion? That means constructing a skyrmion vector texture by the Stokes vector. The Stokes vector characterizing all the polarization state. As we know, all the polarization states can be mapped on a Poincare sphere and with right-hand, left-hand circular polarization state as eigenstate mapped on 2 poles, and all the elliptical polarization on the intermediate surface. So the spin and polarization actually is a bidirectional mapping. All of that can be mapped on a sphere. And now we apply a skyrmion mapping on the polarization Stokes vector. We can get a polarization pattern and emulating the spin texture. So this is a Stokes skyrmion. This concept is similar to our recent hot topic of vector vortex beams. If we superpose the 2 vortex beam with vortex phase and opposite polarization, RCP, LCP, we can get a polarization pattern, spatially invariant polarization pattern. However, this is not a skyrmion. Why? Because it's very beautiful vector beam pattern, but they are only linear polarization distribution, right? The skyrmion required all the polarization state to be observed, to be localized on this region. So how to deal with? The method is simple. If I break the Lie symmetry of the superposition of the vector beam, the OAM, optical angular momentum, and the spin angular momentum of polarization, we break the limit on the superposition, the plus and the minus L we introduce different, for instance, the 0 for representing the Gaussian mode, and then we superpose the non-separable superposition again. We can observe all the polarization states emerge in the region. So this is a basic idea of constructing a Stokes skyrmion, right? Okay, skyrmion has diversified topological states. So the next next work, I will introduce the high-dimensional structure lights to replace the single vortex, right? Okay, here I not only introduce the orbital angular momentum as azimuthal index for controlling the mode, I introduce the Logar-Gaussian mode with also the P mode, the radial indices, together with the intermodal phases. And now we shape the OEM, we can control not only the hedgehog Skyrmion also with the increased number of vorticity with the increased number of topological number. On the other hand, when we shape the radial indices, we can shape the radial reversal of the spin texture as corresponding to a skyrmionium texture that's in the solid state beta, and also radial reversal target skyrmion. And with also high topological number control. All of these are predicted in the solid state physics, but now we can shape that in the optical field. And actually, the Skyrmion mapping carries the idea to control, diversify the topological state with mass space to explore. In addition to the above shown the result on skyrmionium with a radial reversal and with the neo block type anti-type control. We can also have an interesting state with a bimeron. We can shape, for instance, we incline the parametric sphere in the mapping, and then we get the two merons on the skyrmion. Two half skyrmion can be shaped with flexible percent. That's a bimeron. And I will also can apply the radial index in light beam to get some more interesting bimeronium. So to explore, yes, there are always some method to explore space for you to explore new topology in the for both solid state physics and the optical field, right? And it can, all this can be designed in the optical field. And next, I will show our experimental results, experimental method. We can not only theoretically design, we can actually precisely control that in experiment. The method is using a spatial light modulator that can be the liquid crystal based, that can be micromirror based. Anyway, we can use that to shape the light mode. And now we can we use the SLM mask as two part. We split the mask into two part. That's the blue and the green part. The two spatial mode was shaped as on demand for the two component for the RCP and LCP component. And after that, we use the interferometer to superpose these two mode together, and we generate a spatially varied polarization pattern. Now here's the result of our in our experiment. We can measure. We then retrieve the Stokes parameters and get a spatially invariant pattern. And now we can control the above mentioned hedgehog-like texture, vortex texture, and the sidle-like anti-Skyrmion texture. Importantly, this is digital control, digital holographic control. That means we can freely control the transformation between each topological states from the hedgehog-like and to a block-like, vortex-like, and even the hedgehog to the sidle texture with the changing of topological numbers. Okay, after achieving this, I was thinking about a new model to guide us for the topological transformation of all the Skyrmion states. And okay, our light was designed by the Lagrangian modes as related to the Poincare geometric model. So I call this new model as a Skyrmion Poincare model. It's also a Poincare-like sphere, but it's not for OAM. It's not for polarization, but for the spin textures. Okay, now we can see from the equator is representing a transformation between a neo-state skyrmion heterolike to vortex-like block skyrmion with preserved topological number. But if we go through this the surface to the pole, they will transform into the sido-like texture with anti-skyrmion. Always the sido-like texture on the pole. There are 3D spin textures. That means the only 2D surface cannot completely represent all the states. That means that if we go through into the sphere, and you will get the boomerang transformation. This is also a topologically protected transformations. So all the states, all the skyrmion boomerang state can be beautifully mapped on the geometry model. Okay, after the study of topological transformation, we also studying some very interesting property of topological protection in our optical beam. We show that in our optical skyrmions, the optical skyrmion can still show some topological stability upon propagating in the free space. If you design the Stokes skyrmion texture using our method, on the transverse plane, you get the skyrmion pattern, and the light field can be can propagate along the z-axis, and no matter how long it propagates, actually, then each cross-section, the topological number is very stable. You can see the skyrmion number cannot be changed, protected from propagation. And in addition to the free space propagation, we also have some interesting study on the propagating in the nonlinear medium. In a nonlinear conversion, frequency conversion crystal, nonlinear crystal, we input our skyrmion beam, and through we find some interesting conditions. Even the frequency was converted. The spatial skyrmion topology can also be very stable, right? I think these are very fundamental studies for the topological protect in optical information transfer. It's very useful for our future resilience and information network. However, to realize this dream, there are still a long way to go. Because you know, we can freely construct and generate skyrmion, but it's from very bulky spatial light modulator system. So to apply this interesting topology into practical information society, I think the next stage, we think how to shrink the size, how to make a compact devices to generate diversified skyrmion texture, right? For instance, from fiber integrated silicon photonics or microring laser. Anyway, there's no work was done, I think, but I think I have some preliminary work on this. I share this idea with Professor Martin Booth in the Oxford University, and they show me a very interesting devices. It's just like this. This not a fiber, not as thin as a fiber. It's as a very thin rod with the on the cross section. You can see some gradient index, and this is as by gradient barren fringes, and this rod can be connected, can be cascaded by some other optical elements. It's a very compact device, and we can control the twisting angles between the elements. Now we can shape diversified skyrmion with topological transformation from this very compact device, right? And for if we have only one rod, it will shape the skyrmion to the skyrmionium, and with the topological transformation polarity control. And if you have a two rods, you can have you know, the multi-real skyrmionium, and we have one other row cascaded, complex cascading. You can have a multi-skyrmion, the quadruple like skyrmion, also quadrilateral, and even complex Skyrmion. All that's the high topological charge Skyrmions, they are from very compact devices, and we are now still working on how to use this compact device to apply in practical information transfers, optical communication using our Stokes Skyrmion light. Okay. Yes, I think I skipped this some proposal to using the Skyrmion into our practical optical information transfer. Okay, it's very exciting for the Stokes Skyrmion, right? But however, I would like to show that there are still limitation on this Skyrmion. No matter how we shape the Skyrmion, they are all supporting the monochromatic continuous wave vector beam, right? So next idea is how to shape a Skyrmion, control Skyrmion in a spatial temporal pulse, a structural pulse, electromagnetic pulse propagating at the speed of light. So this we call the flying Skyrmion. Actually, this idea is very challenging because in our textbook, we know that the electromagnetic wave propagating in free space are transverse waves. That means the electric field vectors and magnetic field vector are oscillating as the analog of dipole, electric dipole, with only transverse components. These are impossible to shape a Skyrmion because the Skyrmion requires 3D vector, 3D full azimuth vector, right? Luckily, the recent advances of metamaterial highlight some exotic multiple excitation. For instance, the toroidal dipole excitation. The electromagnetic fields as a configuration of solenoids, the toroidal solenoid. And if we can find the counterpart of the propagating solution of the such a toroidal dipole, that's a possible. This may produce possibility to shape Skyrmion. Actually, this was theoretically solved many years ago by the method of space-time non-separable solution when solving Maxwell equations. If we use the endorsed variable separation separable solution to Maxwell equation, the space-time terms are separated, and it will solve the transverse wave. But if you solve the space-time non-separable solution for the wave function, you can possibly solve the exact solution for the flying donut, the flying toroidal excitation solution in free space. And however, the experimental observation was only reported recently by our group. Our method was it's in a two-stage scheme. The first stage, we convert ultra short pulse into a radially polarized pulse by a radio polarizer. The next stage, we convert the radio polarized pulse into a metal surface, and the metal surface would act as a space-time correction, correcting the variable color component. The inside was response to the blue component, and with the radial gradients, the outside was response to the red component. So from blue to red, every colors diffract at the same rate as the iso diffraction configuration. So each color are not separable with the spatial divergence state, right? Like this, and this very similar to the concept of entanglement, but now it's not local 2 degree of freedom, non-separable with each other, the wavelengths and the spatial divergence. In comparison, if we focus a common kind of pulse of the Logar-Gaussian mode, and we know that the various colors can be focused on different degrees. So this will not have a very good necessarability. So we can use the quantum-like method to characterize the fidelity to guide our actually experimental generation of optimized the flying donut field. If we remove the matter surface without the space-time correction, we get very low fidelity. Every colors will mix together. But if we have the matter surface to do the space-time correction, we can have a very good space-time coupling. It's a very good non-stability with a very good fidelity. And this guide us to generate our very good flying donut pulse. Okay, the most interesting property of the toroidal pulse existing in the electromagnetic field. These are non-transverse pulse, non-transverse waves. That means if we have azimuthally polarized electric field, like two-donut field, and you will get non-transverse magnetic field with not only transverse component, the longitudinal components. And you will have many interesting vector singularities on the cross-sectional magnetic field. Due to the symmetry, cylindrically symmetry, actually the vortex singularity on nearby the pulse have a very interesting configuration of vortex ring. It's a configuration frequently studied in fluid and the smoke ring and the air, in the fluid dynamics and air dynamic. But now it's a very initial or firstly studied in the electromagnetic field. Okay, where's the skyrmion? Skyrmions are coupled with the electromagnetic vortex ring. When we observe the front and end cross section of the vortex ring, you will have two kind of skyrmion texture with offset helicity. Okay, I ask the question again. Can we generate more skyrmions with diverse topological states? Okay, this pushed me to generalize the theoretical model from toroidal to super-toroidal pulses. In the original theory, the toroidal problem should be solved under the finite energy assumption with a factor alpha equal to 1 for simplification. However, if the alpha is no less than 1, we can also ensure the finite energy. And the alpha can be as the high order indices to drive the higher pattern in electromagnetic field. As you can see, the singularity on the electric field with the increasing of alpha showing the fractal-like extension, layer by layer singularities, just like a matryoshka-like structure. So, okay, we can observe the multi-layer donuts with the matryoshka electromagnetic field. And we observe the skyrmion again, or we can control the radial reversal orders, and from skyrmion to skyrmion to tertiary skyrmion, and with the increasing of alpha. And more interestingly, the spin reversal occurred at the very tiny, very small region, deep sub-wavelength features, right? And please note that I use the Q1 rather than lambda. The Q1 means the single cycle wave limit. It's a very short and a very small region. And if this feature can be characterized and with the control super-toroidal order, this must be very useful for the resolution enhancing the actual optical metrology and the related technology. And these are our experiment result. We observed such a kind of skyrmion textures in our experimental toroidal pulse. We are still improving the experimental technology to control the super-toroidal order. But the initial case, the fundamental toroidal pulse were already published on the Nature of Photonics. And please refer this for more details. And these are flying skyrmion. That I will deliver the third kind of skyrmion to show that the skyrmion can not only be studied on the cross section on the 2D surface, can also be studied in the 3D real space. And these are 3D skyrmion hopfions. The series are also very classic. The backgrounds are from Hopf. It's a very famous mathematician who proposed the Hopf map, Hopf vibration, hopfion. But actually, the left side of the conventional Skyrmion mapping I just showed. I'm applying the first two kind of Skyrmion and wrapping a 2D, 3D sphere onto a 2D. Point on the sphere mapped on a spin on the 2D localized the region. However, the Hopf map is a higher dimensional map from as a mapping from 3D to 4D. Where is the 4D? So the point on the 3D sphere is no longer map a point on it, but a fiber. It's a loop, a line on the 3D space. So it's if we unwrapping this sphere, initially it's from a pole, it's referring to a ring, thin ring on the center, and then you unwrapping the sphere, you get a layer by layer torus node vibration. It's very beautiful vibration to the infinity, and this is a Hopf vibration. And each fiber act as the iso spin counter. So it's actually it's corresponding. You get the spin texture in the torus, like the 3D space. It's called hopfion. A very beautiful 3D spin texture. And the hopfion can be shaped in light, and the original work theory was proposed by McDennis. And so when we know that when we construct a Stokes skyrmion, we need to break the symmetry of optical momentum. I just showed that in the first chapter in this talk. And now we need to break another symmetry of the radial radial index. If we break this symmetry and we get the complex superposition of vector beam with a longitudinally varied vector patterns. Okay, the polarization pattern, and each polarization can drive state can drive into a fiber with forming a Hopf vibration, and actually this forming the Stokes hopfion, optical hopfion, and the previous 2D skyrmions can be observed in the subspace of the hopfion. For instance, the XY cross section you can observe a skyrmionium texture, and the XZ cross section you get two skyrmions. How to understand it? You just image that you have a skyrmion and you elongate this into a tube and twist him and connect it together. You get this skyrmion. It's a hopfion, and in the cross section you can observe the 2D skyrmion. Okay, the next work I did was I introduced the topological transformation into optical hopfion, and I also introduced the intermodal phase between the logarithmic mode as a component of the vector beam, and the driving the intermodal phase, and we can control the neo type hedgehog and block type vortex, the anti-skyrmion saddle-like texture. All these are subspace of the hopfion. As you can see, what we can do in the 2D skyrmion, and we can apply the transformation vector texture transformation in the 3D hopfion, and these are the experimental result, are very well predicted, agree well with a theoretical model, and actually hopfion can do more things the 2D skyrmion cannot do, because they have the 3D topology that creates new topological order to control. For instance, the PQ. The PQ means how many times a fiber goes through the hole of the layer of a torus, and how many times it goes around the torus and the PQ. And then you can see the 2 times through and 1 time around, and even higher order, 3 times goes through the hole and 2 times around. And these are new topological numbers that in 3D, the 2D skyrmion cannot have. But now we can we can control these orders in 3D structure light, and even interesting. And we show the improved experiment with enhanced precision. Now we combine the front end are similar to the previous 2D Stokes skyrmion, but then now we use a metasurface polarization grating to combine these two beams together. Now it can have a very enhanced persistent to replace the previous interferometer, bulky interferometer. Now we apply the refreshing the digital mask again. Now we refreshing the intermodal phase between these two polarization component. Now we can control the free space transport of the 3D hopfion. You can see the vortex ring like hopfion can be transported in free space along the z-axis. And I think this is the first time the 3D topology, the hopfion, the previously predicted in the solid physics, now can be transported in free space in light. And I think this is a very emerging direction to explore. Because in we know the 3D opens the door to control high dimension topology and with even high order topology order that's to be controlled in our optical field. And I also highlight that there are many other kind of 3D quasiparticle in addition to the hopfion, for instance, the boron. I think that's proposed by Professor Evan. It says it's also toroidal like spin texture, but with the two singularity like monopole. And helinoton is not even fancy. It's something that as the torus nose invariant Skyrmion texture. And there are many other kind of 3D quasiparticle are to be explored in optical field and interact with our optical field. Okay, I think it's time to do a summary. I introduced the three kind of free space skyrmion. And the first one is the Stokes skyrmion with the topological transformation and digitally controlled and the topological protection property. And the second one is a flying skyrmion that can be existed in toroidal light pulse with non-transverse, separable, fractal singularity, deep sub-wavelength feature, many physical property to be explored. And the skyrmion can be shaped not only studied in 2D, but also 3D, and even high dimensional quasiparticle to be explored in the future. And finally, I would like to say optical skyrmion, a very promising concept. And the community are booming because it carries the idea of controlling diversified topological order, topological stability in the ultra small, ultra fast region, and these will surely revolutionize our optical technology for our advanced photonics. And as a final slide, I did a perspective. Let me do a perspective on this future. These are the fundamental idea of the skyrmion, right? A mapping from a 3D sphere to a 2D. On one hand, in theory, we can extend the theory into higher dimension. And the whole, we know that 4D maps will generate a hopfion vibration. And then how about the even higher order? How about the link between the hopfion in 5D in the future? And many high dimensional topological states are theoretically to be studied, right? And when having this mapping, how to apply that to optical field? Firstly, we need to select the optical vector, right? In this talk, I introduced the electric field as a vector to shape the flying skyrmion, the Stokes vector. And there are many other kind of optical fields, for instance, spin, angular momentum, pseudo spin, pointing vector, who knows? Many other vector can be used to apply this mapping into the optical field. Okay, where to apply this field? We can apply the mapping in the space-time to generate the skyrmion pulse, and we can generate in the apply it in the space, generate plasmonic skyrmion and the spatial skyrmion. There are also other kind of physical domain, for instance, the K-space in photonic crystal, right? And also non-local entangled space, or other synthetic dimensions, Zenic dimension, while many other space are to be explored. So I think in the fundamental physics, there's still many space to explore, and once we controls diversified the topological order in such a small dimension, and the many application can be applied and can be extended using the Skyrmion. For instance, so we have the deep sub-wavelength feature for ultra-fast, ultra-small imaging, microscopy, metrology beyond the current resolution limit, and if we can control the topological orders in propagating beams, that can be used for more resilient optical communication with the new topological order to as an information carrier to ultra high capacity, the robust, ultra resilient optical communication network. And then finally, I would like to say the idea come from solid state physics, right? But how now we can have the topological excitation in free space light. Now, how about to interact that with solid state, right? So we have made the new topological configuration in light may excite some the excitation in materials, but that cannot be excited, not easily to be excited by previous planar wave illumination. So if you, I also write a perspective paper on this optical skyrmion, also recently accepted in Nature Photonics to be published. So welcome to follow. Okay, thanks for the related funding, and actually I have many other kind of stories on structural light in my group, and in addition to the skyrmions, we also have the Rayleigh coupling multi-degree freedom and some metamaterial design structural light. So welcome to follow my website to find more my story of exotic structural light. And I'm establishing a new lab in Nanyang Technological University, Singapore, and there are some opening positions. Welcome to apply if you are interested in, and I hope we can do together further exploration on exotic structural light. Thank you very much.